Hello, welcome back. Last time we introduced Huffman coding, and we showed that Huffman code is optimum, but it's optimum in the sense that we limited ourselves to code one sample at a time. And it turns out that this is a pretty big limitation, and that's why most of the time Huffman coding is actually not the best approach to use for source coding. For example, if I have a source, let's say X is the outcome of flipping a very biased count. Let's say it can take head and tail, and the count is so biased that the probability of head is basically 0.99 and probability of tail is 0.01. So if we compute the entropy of X, the Shannon entropy of X will be approximately equal to 0.09, something like. But if we try to build a Huffman code for X directly, what we see is like, okay, we have head and tail. The only thing we can combine is these two. And so therefore the code word for head and tail would be just 0 and 1, or like 1 and 0. In other case, we can only compress the source to 1 bit per sample. Or in a sense, we are not compressing the source at all. However, we know that like in theory, actually we can compress the source to a weight about like 0.09 bits per sample. So therefore, this Huffman coding in this case is not so effective at all. Okay, of course, one thing we can do is just combine several symbols into a block. For example, if instead of coding one sample at a time, let's say we code two samples at a time, so I just make up a super symbol, like let's say HH, HT, TH, and TT, and I know the probability of this super symbol will be like HH will be approximately 0.98, I guess, and HT will be something like 0.01, and TH the probability about 0.01 also. TT is about like 0.0001. It should be 0.0001. And if we build a Huffman code for that, it would be something like this. And let's assign some code word for that. And then the code word for this super symbol head will be 1. For head tail will be 01. For tail head will be 001, and tail will be 000. And we can see that the expected length will be approximately equal to let's say I give a index 2 here, just to remind ourselves that we are coding two samples at a time, and that is approximately equal to 1, as we can see. So it's 1 times 0.98 plus 0.01 times 2, that's 0.02, and plus 0.01 times 3, there's another 0.03. So anyway, it's like an order of magnitude, like 2 order of magnitude smaller than 1, so therefore like we can't ignore that. Probably this is 1.03 about, something like that. But in any case, it's pretty close to 1. And of course, okay, wait a second. The expected length seems to be even bigger than what we have previously. But remember that like we are coding two samples at a time, so therefore like per sample wise, we are actually, the weight is really about like 0.5 bits per sample. So okay, we are indeed code more efficiently than before by combining two samples at a time. But it's still like quite a bit far from like the theoretical limit 0.09. Of course, we can keep doing this. Like we just pack more, like combine more symbols, more samples at a time for each block. So we just code, for example, like 3 samples at a time. So we have head, tail, and so forth. We have a combination, and then we build a Huffman code for that these super symbols. And again, like and so forth. But the problem is, now if we do that, we can see the complexity just goes up. In particular, basically the Huffman coding is encoding and decoding is just based on table lookup, right? After you're building the code, you just look for the code word that you have, or look for the entry in the table that is correspond to your input symbol, and then you output the code word. So each time you pack one more symbol, basically the capacity just double. And of course, this is not very designable in practice. And another problem is like when we build this table, we need to build this table beforehand. So it's kind of like we know the statistics beforehand. That is kind of okay. But in the sense if your statistics of your source is changing, then it's actually pretty hard to go back and modify this table. In a sense that it's hard to, I shouldn't say impossible, it's harder to build like adaptive Huffman coding. And that motivates us to look into other kind of source coding scheme. In particular, actually the de facto scheme for source coding, or like people like to say entropy coding, is arithmetic coding. And we will talk about arithmetic coding later on, but in this segment we will focus on something called SFE code. It's Shannon-Fano-Elias code. So you can consider this as a precursor of arithmetic coding. SFE code itself is not very useful actually, but it's useful in trying to understand arithmetic coding. Okay, the idea of SFE code is quite simple. Actually, it's trying to map any binary sequence into an interval between 0 and 1. So basically, if I have a binary sequence, I can think of a code word, let's say 101, that I will map it into an interval 0.101 to 0.101 1, so on. Or I can write this as 0.1011 dot, something like that. Oh, note that these numbers I'm showing here are in binary, so therefore like 0.101 is actually, this is like 0.5 plus 0.125, this 0.001 is 0.125, so this is 0.625 to basically 0.1011 all the way goes to infinity. It should be like equal to 0.11. That will be correspond to 0.75. Let's look at a couple more examples. So, for example, like for code 0, that will be simply mapped to interval 0.0 to 0.01 dot. That will be like from 0 to 0.1, maybe 0.1 in binary, and decimal will be like 0 to 0.5. And another example, let's say 1 that will correspond to from 0.1 to 0.11 dot. That in binary, that's basically 0.1 to 1, or like in decimal would be 0.5 to 1. So let's give one more example. Let's say 10, that will be correspond to 0.10 to 0.101 dot. That is 0.10, 0.11, and that will be from 0.5 to 0.75. One thing we can see is that the width of the interval increases as the length of the code decreases. So actually, more precisely, let's say if I call denote the width of an interval as W, W is basically equal to 2 to the minus L, where L is the length of the code word. So actually, the width decreases exponentially with the length of the code word. Another thing we can observe is that a code word is a prefix of another code word, then the corresponding interval of the first code word will include the interval of the second code word. Actually, this can be very easily seen, right? Because if I have a code word that, let's say, I just write A, B, C, something, and that's the code word, let's say, or like, let me just write some exact number, like, let's say one code word is 101, and another code word, let's say, is 10111, and then the interval for the first one will be 0.101 and 0.1011 dot. Apparently, this will include the interval of this second guy here, 0.10111 to 0.101111 dot here, because the lower bound of this one apparently will be smaller than the lower bound of this second one here, and the upper bound of this one, as this guy here, will apparently be bigger than the upper bound of this guy, that's this one here. So we have A is a prefix of B. It's prefix of B. Then interval of A will include interval of B. Or like, of course, when this interval like include each the other, this interval of A included the second one, I can, of course, this will imply that the intersection of the interval is not zero, or like not an empty set, or like these two intervals overlap with each other. So what does that imply? If that implies that the negation of this statement should imply the negation of this statement, right? So therefore, like, if two intervals not intersect, if interval A does not intersect with interval B, thus the intersection is an empty set, then A cannot be a prefix of B. Of course, for the same argument, B cannot be a prefix of A as well. So now if we consider a random variable, let's say X, can take some possible alphabet of, like, let's say A, B, C, D again. and let's say the probability of A, B, C, D are 0.1, 0.2, 0.3, and 0.4. I can map this probability into the interval 0 to 1, and let's say A will map to the interval 0 to 0.1, and B will be from 0.1 to 0.2, and C will be 0.2 to 0.5. Wait. Sorry, this should be 0.1 to 0.3, and C will be like 0.3 to 0.6, and let's say D is 0.6 to 1. So what I just did is basically assign an interval for each of the symbol, and the length of the interval is proportional to its probability. So, and from what we observe about the code that trying to map a covert to an interval using the construction that we discussed earlier, we see that like I will have a longer covert if my interval is smaller and otherwise. And more importantly, as long as the intervals of two corresponding coverts do not overlap, that two coverts cannot be prefix of one another also. So therefore, if I construct a covert for each of these symbols, and each of them do not overlap with each other, then I can be sure that the resulting code is instantaneous, because none of the coverts will be prefix of the others. So for example, if I just make up, this is like the interval for the covert of A, and let's say this is for B, and this is for C, and this is for D, and because these intervals do not overlap, therefore the corresponding coverts cannot be prefix of one another, therefore the code is instantaneous. And moreover, apparently for my own interest, I would like to have this interval as long as possible, because if it's long, then my covert length will be shorter. And you can also see why I want to assign this width, assign the interval to have length proportional to the probability, or like exactly equal to the probability, because for the more probable symbol, I want to have the covert to be shorter. More precisely, the SFE code will basically select the covert from the midpoint of each interval. For example, for the covert of A, I have like this, the midpoint of interval A will be 0.05, and if I represent this in binary, it would be 0.00001, something like that. And basically, our intention is that we want to make sure that the interval won't go out of bound, right? So if I set that is like basically I want to make sure that P has to be W has to be less than Px over 2. And what we can do is we can set L as a minus log Px over 2 and set the ceiling, and then we can make sure that this will be less than Px over 2. And know that like if we take the exact covert, okay, after we have this computer length of the covert is L, in this case Px over 2 is 0.005 again, and that is like LA will be something like log PA over 2, ceiling of that one is equal to 5. Then if we take the first 5 bits after the decimal place or the binary place, as the code word, then the represented interval will be something from 0.00001 to 0.00001 dot, and that's basically we can easily see that like this will include the include the 0.05. That's the midpoint of A inside this interval of the code word. And of course the width of the code word is less than px over 2 or pa over 2. Therefore we will have something like that, like this is less than pa over 2, and this includes the midpoint. Apparently this interval has to lie inside this the interval of A from the allowed interval of A from 0 to 0.1. So we can do the same thing to generate other code words. So basically we have this code word of A now is equal to code word of A is 0.00001, and code word of B we're supposed to compute midpoint of that is 0.2 in binary. So that one is something like 0.001. Okay, I better use a calculator, I guess. We have 0.2. If I change it to binary, 0.0. Okay, yes, 0.00110. And if we compute log minus log PB over 2, that's LB, that's equal to minus log 0.1. And okay, I don't have a log here, but I can just 0.1. Okay, I think that's 4. So therefore, like that should be equal to 4, and so therefore the code word of B will be like 0.011. Let's compute the other two code words. So for C, I have the midpoint is 0.45, and so 0.45 is basically, again, let me use the calculator. 0.45, so it's 0.1110, 0.10111, and the width of C, the length of the C, code C should be minus log PC over 2, that's equal to minus log PC is equal to 0.3, that's 0.15, so 0.15. So basically this is the trick you can use. Is like if log 0.15 minus log 0.15 is just equal to the how many digits after the binary place. So this should be equal to 3. So therefore the code word for C should be equal to 0.11, and for D, okay, D is a from points. The midpoint of D is, let me just use here, is 0.8. 0.8 is 0.110, and LD is equal to minus log PD over 2 is 0.2, so that is equal to 3 again. Let's see, yeah. So, okay, so I should take 3 digits and therefore CD is equal to 110. So that's basically the SF equal. So we can see that I need more space, I guess. Maybe I can just use here. Quick, tiny space here. We can see that the average length of the covert is given by minus log px over 2. I mean, for each of the covert, the length of the covert is given by that. So therefore, like, it's bounded by minus log px over 2 plus 1, and is bounded by minus log px plus 2. Actually, it's just equal to minus px plus 2. So therefore, the expected length is just like expected minus log px plus 2 is equal to h's plus 2. So we have in maximum 2 bits loss from the theoretical limit. That's basically the Shannon entropy when we use the SFE code. So it's not really spectacular, it's pretty big loss really. But as I mentioned at the beginning, SFE code is useful to understand a more useful code, that's so-called arithmetic coding, that I will talk about that in the next segment.